Welcome to Codesmith, JavaScript, the hard parts. Today we're going to be talking about some recursion, kind of a web dev fundamental. This whole series focuses on some fun concepts like higher order functions, callbacks, recursion, closure. Tonight we are specifically diving into recursion, but if any of that sounds interesting, feel free to check it out. My name is Rebecca. I am a Codesmith graduate and former instructor, and I now work full-time as a software engineer elsewhere at Rent the Runway. So if I can do it, you can too. I am not only not from a technical background, I also have dyslexia. So on the best of days, I can't even read well. On the worst of days, I'm a former hand model. So, if I can do it, literally any of you can do it. I have the most untechnical background of anyone here probably. But welcome. Let's dive right in. What is recursion? Kind of a tricky question, but hopefully you will leave here tonight feeling a little bit better about the answer to that. But before we dive in, does anyone want to take a stab at answering that question right now? What is recursion?
It is a function that calls itself.
Beautiful. Daniel, do you have something different?
Well, yeah, recursion is recursion is recursion is recursion.
You've been here before. Daniel.
Yes, I have.
Daniel, that's my favorite
I heard that
joke.
from you, actually.
Damn, Daniel. How dare you? Oh my God.
Had to steal the thunder.
Joke. Oh, I'm so sad now. Yeah, recursion is recursion is recursion. My thunder is gone. Okay, well, a fancy definition might be that recursion is a method of program design where you break apart a problem into smaller, repeatable subtasks. So the program will complete each subtask, and then it will later combine those subtasks to achieve a solution. Yeah, my favorite answer is that it's recursion is recursion. Thank you, Daniel. But aside from being a big part of the Codesmith technical interview, recursion is also a pretty big important concept of computer science. So this interview, or the CSX unit for it, whatever, is probably the first time you'll see something like a function calling itself within its own function definition. But recursion is not just a JavaScript thing. It is a whole paradigm of thinking that you could adopt and use in many different programming languages. It also doesn't just show up in the Codesmith technical interview. It is a common thing that you will see pop up in job interviews as well. But it's not something super common that you would see within, say, a production code base. So recursion is a little bit of a tricky mistress. So Miss Recursion, I feel like a lot of algos that you see that require the use of recursion are pretty fancy, pretty discrete, solving mathematical formulas. It's not really something that you would maybe go throwing around willy-nilly in your code base where you have to make a user. It's kind of, you wouldn't want to keep making users indefinitely. You would run out of storage and space, and your database would yell at you pretty quickly. So it has most of its use in algorithms, which is what interviews are mostly made up of. But how much do you actually see this on a day-to-day job? A little bit debatable, but that's fine. But Miss Recursion, she's a little bit dangerous and a little bit mysterious. You kind of got to know what you're doing with recursion, or you can blow your call stack and have a ton of unwanted side effects. It's kind of a chaotic neutral character. But if you use it correctly, it is a great tool for writing more intuitive, declarative, and maintainable code. Hopefully, we will see some of that here tonight. But before we go diving into the nitty-gritty of recursion, we're just going to cover a few basic fundamental things related to JavaScript and just general programming. So first, we have our thread of execution. I saw recently someone call the thread of execution the toe, because T-O-E. I hate that. Don't do that. Don't call it the toe. The thread of execution. So JavaScript itself is a single-threaded and synchronous language, which means it can only ever do one thing at a time. So it starts from the top of our program and it works our way down to the last line of code. You can kind of think of it as holding your finger as you are reading. So you can only read left to right, top to bottom, one line at a time. I can't skip down to this line until I have finished with this line. Pretty simple concept, but some languages are multi-threaded. It gets a little bit hairy. That's always fun. There's also some ways that you can kind of force JavaScript to be asynchronous. But again, can of worms, we're not really going to get into that here. But as our code is being interpreted, we need a place to store important information, such as function names and variable identifiers. So for each active execution context, beginning with global, we are given a special variable memory environment memory to store things like variables. So for example, let's say I wrote num equals 7. I would need that label num to get saved into memory so that later on, whenever I reference the variable num, JavaScript knows what I'm talking about and it can update the value to be 7, whatever. And then if I go back and I decide that I want num to now equal 9, I need it to know first, go back into its memory, see what num used to be, and then update it, and then be able to reference it later. Or I could save this function definition, multiply by 2, under this label, multiply by 2, so that then whenever I go back and I reference multiply by 2, JavaScript knows kind of what the heck I'm talking about, and it can actually execute this code because it's able to look into its memory and see what I'm talking about. Next is functions. If you're not familiar with functions, they basically just allow us to bundle up code later for repeated use. They help us to keep our code dry. Let's see, who knows what dry stands for?
Don't repeat yourself.
Hank, go for it.
Don't repeat yourself.
Hank, go for it.
Don't repeat yourself.
See, I'm making a very funny joke. Daniel, you can't get me this time. Dry, do not repeat yourself. Wasn't that annoying? It's never fun whenever someone is repeating themselves. Also, if we were in a code base and I was making him type, do not repeat yourself, that's like 4 or 5 lines of code that I made him repeat over and over again. It's not doing anything for anyone. So we don't want that. We don't want our code to be repetitive. We want it to be nice and general so that we can reuse it as the case for use changes. We can just plop in different variables, different parameters, and reuse the same piece of code without having to rewrite the function every time. Saves us a lot of time and space. Speaking of parameters, who here can tell me what parameter they see on the screen right now? Gail, go for it.
N.
N, beautiful. And how do you know that N is the parameter?
Because it's what's inside the function definition parentheses.
Okay. Who can tell me what the argument would be in this case?
It would be 4.
4, beautiful. So a parameter is just a placeholder that we use at the function definition that we are later going to substitute out for a real value at runtime. So when it's being defined, we have a placeholder of n because we don't know what n could be. It could be 4, it could be 12, it could be 42. We don't know what this is. It's just a placeholder at the time of writing the function definition. Then whenever we see down here, this multiply by 2 function being invoked, we see these parentheses here. That means it's runtime, baby. It is time to substitute our parameter for our actual argument, what we are actually calling the function on. So they were absolutely correct. This up here, n is the parameter, 4 is the argument. Is that cool for everyone before we move on? One of the first things that we have to do in all of our diagramming is to match our arguments to our parameters. SQ, question.
Yeah, sorry. I know what the parameter and argument is, but you said it in a specific way, and I know you guys are like big on technical like communication. So can you repeat what you said how you said what a parameter is?
Of course. A parameter is a placeholder that we use during the function definition that later gets substituted in for our argument.
Well, I appreciate it. Thank you so much.
All good. Does that answer your question fully?
Yeah, it does.
Okay, cool. So yes, the fancy way of saying it is this is the placeholder that we assign at function definition that we later substitute in with the actual argument during runtime. So cool. Cool. Okay. So when we invoke a function, a new function level or active execution context is created, and our active thread of execution jumps inside of that new active execution context to run the code within a function definition before continuing with the rest of the outer context's code. That sounded confusing, but the thing that is keeping track of all of that is the call stack. So as I am adding function calls to my global, they're getting put onto the stack to keep track of what execution context we are in. Because as you heard, just hearing the process of it, it's a little bit confusing. So having a place like the call stack to keep track of it all is going to be helpful. The call stack is also important with recursion because when you have a function that is calling itself, and each time a function gets called, a stack frame gets added to our call stack. If you mess something up in your recursive loop, you could keep adding stacks indefinitely, blow the stack, get a stack overflow. The whole site gets mad at you, times out. No one likes that. I'm crying, you're crying, the computer's crying. No one likes a stack overflow. That's why they named the website after it. It's a super common thing, big problem. No one likes it. But okay, we can see all of these 4 things in action here in our little warm-up demo. So let's just walk through this multiply by 2 function here. Can I get a brave volunteer to walk me through this?
So we're declaring a function with the label multiply by 2
Okay,
that takes in the parameter n to global memory.
by 2 to global. I don't actually care about the parameter at this point. I just need to know that this is a function.
Mhm. Okay, and then we're gonna declare a constant variable with the label output and set it equal to the value of the evaluated result of the function multiplied by 2, and set that into global memory. Yeah, with the argument 4.
With the argument of 4. Okay, so before we move on to what is actually happening on this line, does anyone know, Daniel, maybe you can answer this yourself. Why did you skip from this line to this line? Anyone want to take a stab at it? Ian, I see you nodding. Oh, okay, there's the hands. I missed it. Never mind. Never mind, Ian. Tammy, go for it.
Because the function hasn't been called yet.
Correct. I'm just right now, I'm JavaScript, I'm the thread of execution. I'm just reading left to right, top to bottom. I see function. I don't really care what this does. I'll just save this definition later in memory so that whenever this function gets invoked, I know what to do. I don't really care what that function definition is. I just need to know it's a function. So I see function multiply by 2, put multiply by 2 as a function in global memory. Then I skip right along to the next line of code, which happens to be this const output. So I add output to my global memory. And then Daniel said this beautifully. The assignment of output is actually the evaluated result of invoking the function multiply by 2 on the argument 4. So we don't know what that evaluation is until we actually open up an execution context, put something on the call stack, and then dig in and see what this result is. So Daniel, you're doing great. Take it away. What happens now? As soon as we see this function get invoked, what chain of events gets kicked off?
Yeah, so once we invoke the function, we're going to go into multiplied by 2 and go into the local execution context. And
okay.
Oh yeah, also push it into the call stack. And
Right.
We're gonna start looking into the function, and we see that we'll pair our argument with our parameter.
Beautiful.
And we'll look at our return statement and return 4 times 2, which is 8.
If we were to slow it down, if we go back to that first step you said of pairing our argument with our parameter, what's our argument? What's our parameter?
Our parameter is n and our argument's 4.
Okay, so we pair those. So now we know anytime we see n inside this function statement, it's going to be 4. So that makes it easy on this next line where we have to return n times 2 instead of n. We're using 4. And what is that result?
8.
Beautiful. Bet you didn't
And then
think
we'll
I'd make-
store that 8 into the global memory into the output constant variable.
Right. Exactly. So we have to do some evaluating here to see what actually is the result of invoking multiply by 2 on the argument 4. We come in here, we see the return value from this function just spits out directly 4 times 2. So the thing that gets returned is just the value 8. So our output is now assigned to 8. What happens now, Daniel?
I think we pop off the multiply by 2 function out of the call stack and make it eligible for a garbage collection.
Absolutely. So we hit our return. We are done inside of this function. that means it is time to garbage collect. All of that happens under the hood. As soon as we are done running this function, we are able to just throw all of this away. We don't need to keep track of this local memory. There's not a reason really for JavaScript to keep track in this file of what local memory n equals 4 is. As long as we know that output equals 8, that's good enough for us. So we are free to garbage collect this. Okay, not bad. Nice warm up. Hopefully that was gentle for you all, but are there any questions, comments, concerns? Are we already screaming, crying, throwing up, looking at this? Anyone? Let's move on then. Sounds good to me. No, don't put the chat there. Let's go back to our slide and see what's up next. Okay. So now let's talk about some repetitive tasks. So repeating tasks is incredibly common in JavaScript. So common, in fact, that we have special keywords for it, like while and for, that help us simplify this. So using things like a for loop and a while loop let us do things over and over and over again. And this is called iteration. So whenever we do something iteratively, we need at least 3 things. We need an initial value, a breaking condition, something that tells us to stop running the loop, and an update expression. So something that is going to take that initial value maybe from one state to another so we can get closer to the breaking condition. So who can tell me what the initial value on the slide is? Jose, go for it.
The initial value is result equals 0.
Not quite. Good guess though. If you had to take another guess at what it is, what would you think the initial value is?
No, it's not. No, it's n.
It's n. Beautiful.
I was not looking. Yeah.
That's all good. You see the assignment. It's like a nice reflex to say, like, it must be that thing, because that's what's getting, like, something's happening with it here. So maybe it's that. It wasn't a bad guess at all. But in this case, the initial value is n. Who sees our breaking condition? Carolina, go for it.
Hi, so Carolina here. The breaking condition will be if n is greater or equal than 1.
Correct. So what we are only going to run this while this statement here is true. As soon as this is not true, break the loop. That is our breaking condition. Beautifully done. And who sees the update expression? Marcy, go for it.
That would be n equals n minus 1.
Beautiful. This is what is being updated to get us closer to our breaking condition. So again, the 3 things: initial value, breaking condition, and update expression. Without these, we get some odd, unpredictable behavior that occurs and our program won't work as we're expecting it to. So does anyone have a guess as to say what would happen if we didn't have a breaking condition? Owen.
A stack overflow.
Yeah, we wouldn't break. We would just keep going and going and going. We wouldn't actually have a stack overflow in this case because we're not actually adding things to the stack here, but we would have an infinite loop. So same idea. We would just be running this loop again and again and again until we hit infinity, which we wouldn't hit because it's infinity. So our computer would just get very mad at us. What would happen if we didn't have an update expression?
We would have another infinite loop, right? If there's no update expression, you said?
Yeah, it would just keep like running it again and again. It would either do an infinite loop or it would just run it the one time. It'd be like, what do you want from me? So sometimes, I don't know. It would just depend. I actually don't know. Something weird would happen. Something weird and unintended would happen is the answer. And if we didn't have an initial value, obviously nothing would happen because we don't have an initial value. Okay, great. So now they have a solid understanding of iteration. So let's see what happens whenever we try and get the sum of all natural numbers. And all that means is, like, if you were to take the sum of natural numbers with 3, then we just add all the numbers between 1 and 3 because you don't have natural numbers beyond that point. So the answer for some naturals of 3 is 6 because 1 plus 2 plus 3 is 6. So let's walk through this code together. Who wants to volunteer to do this one? Rodrigo, go for it.
Okay, so hi. The first thing we would do is we declare a function with the label SumNaturals in global memory, and we assign to it the function definition within the curly braces.
Okay.
And then
Sounds
the
good.
next, yeah, perfect. And then the next thing we do is we declare a constant output and assign to it the evaluated result of invoking the SumNaturals function on the argument 3.
Perfectly said. Beautiful. But we don't actually know what this evaluates to yet, do we? So what happens as soon as we invoke that function?
So it's temporarily undefined, and we push a call to SumNaturals to the call stack, and we create a local execution context.
Okay. Thread of execution enters this local execution context, and what happens?
And there the first thing we do is we store in global memory the value of the passed in argument 3 as n, right? So we assign to n the value of 3. And then the next thing we do is we declare a local variable result, and we assign to it the value of the number 0.
Perfect.
And then we enter a while loop where, as long as, well, and then let's just dive into it. So into the condition. So it first checks if n is greater than or equal to 1, and is currently 3. 3 is greater than 1, and so it evaluates to true. And we therefore enter the body of the function where we update the value of result to the sum of result, which is 0, and n, which is 3. 0 plus 3 is 3, and so we update the value of result from 0 to 3.
Okay. Perfect.
And the next thing we do is we update the value of n to n minus 1. We're basically decrementing the value of n, which is, so 3 minus 1 is 2. And so now n is 2.
Okay. That is now a 2. I'm going to cross this out. All right, cool. What happens now?
Yeah. Now, since we ran through the body of the while loop, then we start again, and we first check if the condition, the breaking condition, is true. Well, we evaluate the breaking condition, and so we check, is n greater than or equal to 1? N is 2. 2 is greater than 1, and so it evaluates to true.
Okay.
And we therefore dive into the body of the while loop again.
All right. So what happens inside the body of the while loop?
Yes. And so same as last time, we update the value of result to the sum of result and n, and result is 3 and the n is 2. So 3 plus 2 is 5. So we update the value of result to 5.
Okay. 5. Beautiful.
Yeah. And then the next thing we do is we update the value of n to n minus 1. N is 2. 2 minus 1 is 1. And so now n, we update it to 1.
Okay. All right. Cool, cool. What happens now?
And the next thing we do is we check if the breaking condition, we evaluate the breaking condition once again. And once again, n is greater than or equal to 1. 1 is equal to 1, and so it evaluates to true. And we once again dive into the body of the while loop.
You're doing fantastic. I'm being a menace right now. I apologize. Hold on, just catching up with you. Okay, here's my new block. Oh, I lit all of it. Oh, I'm so sorry. You're doing beautiful. Okay. So you said n is now 1.
Yes.
So we do this little conditional check. Is 1 greater than or equal to 1? Yes, it is. 1 is equal to 1. So we move into the body of the function where result gets reassigned. So what happens to result?
We reassign result to the sum of result and n. N is 1, result is 5. 5 plus 1 is 6. And so we update the value of result to 6.
Beautiful.
And then we reassign the value of n to n minus 1. N is currently 1. 1 minus 1 is 0. So we update the value of n to 0 in local memory.
Okay. Now what happens?
Now we once again check the breaking condition. And this time 0 is not greater than or equal to 1. And so that evaluates to false. And therefore we exit the while loop and we return the value of result, which is 6. And so what happens here is the value of result, which is 6, updates the value of output in global memory.
Beautiful. So we return the last valid output we had because this didn't match its check. So what we return to output is result from this line here. So this gets replaced with a 6.
Yes.
Okay. What
And then
happens now?
Yeah, and then we pop the call to some naturals off the call stack, and the execution context, the local execution context, is now eligible for garbage collection.
Beautifully done. That was perfect. I was so slow trying to keep up with you. That was perfect. Okay, very, very beautifully done. Amazing. Anyone have any questions, comments, concerns about what they just saw? Rodrigo, walk us through. It's pretty stunning. I don't have any questions. There we go. Felipe, what's up?
Yes, Rebecca, I have a question. So I know before we said that I get that this is recursion because it's doing the body of the function many times until the condition is met. But in this case, we're not recursing the main function. We're not calling against some naturals, right? So my question would be, is this still deemed as recursive or recursion, or it's not?
It's not. You caught me. This is a warm-up. This is showing you why recursion is better. I made you do it the boring way so you can see the fun way. So yes, nice catch. This is not recursive right here. This is just iterative. So this is just using a while loop to iterate through a function. And the purpose of doing this before doing recursion is to kind of show you how slow and clunky iterative checks are. So like before we can do anything fun, we have to do these 3 steps here. Whereas with recursion, we just call the function and make it do whatever the function is doing. We don't have to bother with all these checks. I mean, we do, but like, you know. So for example, the first thing that we had to do before we could get anywhere else, we had to do a conditional check for everything. So each time that this function runs, we have to say, is n, in this case, n is 3, greater than or equal to 1? We say, yes, it is. So then we have to do some reassigning of the results. Who, I guess we've already gone through this, but just for fun, who can tell me what the reassigning, I guess this would be called the update expression, not reassigning result. What is the update expression here? Gail, go for it.
N equals n minus 1.
Right, so 3 equals 3 minus 1, which equals 2. Okay, and then we have another thing going on here, which is our decrementing of n. Oh, I see. That's why I named it the way that I did. Okay, so this is reassigning results. So we have to reassign result now here too. So we take result from 0 and say 0 equals 0 plus 3. Okay, fine. That's not so bad, but then we have to do it again. So we've decremented, we have this update expression where now n is equal to 2. So we check again, is 2 less than or equal to 1? Is it? Yes, it is. Okay, so we have to go ahead. We have to do our update expression again and say this time 2 minus 1 equals 1. And then we reassign our results. 3 equals 3 plus 2. Okay, fine. Not so bad, but we have to keep going. We have to keep doing this again and again until we get all the way through it. So is 1 less than less than or equal to 1. Yes, it is. It's equal to 1. So we have to, again, hit this little update expression. And we have to reassign our result from 5 equals 5 plus n. Okay, now something fun finally happens. Is that evaluation true? No, it is not. So we finally break out of our loop. Again, not terrible, but there's just a lot going on here with this approach that we can maybe do and handle a little bit better. So let's talk now about what that a little bit better way is. Okay, so again, this first example, using iteration, it's great. It gets the job done. You know, that was our goal, to find the sum of all natural numbers. We did that, but again, it could be better. So this is what you're looking at, this code block here. It's pretty intuitive. You know, most programmers who are familiar with imperative programming, using, you know, for loops and while loops all the time, they'll get this. They'll know what you're talking about here. But thinking about each step, as we just saw, is kind of exhausting. It makes our code a little bit verbose, and it takes more time to really process all that is going on than is strictly necessary. So not only are we wasting valuable time, space, and thought on something like, how am I going to access the data, rather than something a little bit more useful, which is, what do I actually want to accomplish here with the data? So instead of asking, how am I going to do something, we ask, what do I want to do? And then we do it in the fastest way possible. It would be better if we had some paradigm that was perhaps a bit more declarative, that would allow us to just express simply what we want to be returned, instead of, you know, going through all of those obnoxious steps and hammering it home for 5 minutes. If you're wondering, ooh, she's building to something, you're on the edges of your seat. Yes, you caught me. Finally, we are going to start talking about recursion. So as we move forward, some of you might kind of be stumped by recursion, which is totally fine. It takes some time and some practice to really understand what's going on. But with a little bit of effort, you, I promise, will have your aha moment. I know I sat in this workshop a few years ago, and whenever we started talking about recursion, had a panic attack, couldn't handle it, had to turn my camera off and take a step back. It's rough. The first time you see it, it's not the most intuitive thing. You know, had a little monkey playing cymbals in my head. Still do sometimes, but that's okay. We're all here. We'll get through it together. But like Felipe said, we didn't see any functions calling themselves there. We was just kind of doing a loop. So now we're going to actually start seeing some fun stuff, like functions actually invoking themselves inside of their function definition. So a recursive problem is one that can be defined in terms of figuring out a smaller instance of a problem and then using those results to get some kind of desired output by calling itself again and again, breaking it down smaller and smaller until we get to the end result that we want. Again, recursion is my favorite explanation of it. But each function invocation is going to break down the problem a little bit more by repeatedly calling itself to break it down a little bit, maybe shaving an n off, maybe doing n-1 each time you run through it, makes it a little bit smaller each time you call it. So each function invocation is going to break the problem down into a smaller piece. The goal is to break the input down into the smallest possible solution to generate a result. So for those of you who've been here before, I'm sorry, I'm not changing my metaphor. My favorite metaphor, like layman's terms for explaining recursion, is just thinking about like being in line at a taco truck where you join, there's some odd number of people in front of you, you're not really sure, you want to figure out how long it's going to take for you to get your lunch. So you tap the shoulder of the person in front of you, you say, hey, how many people are in front of you? And they say, I don't know, I see just as many like random heads in front of me, I don't know. So let me tap the person in front of me. And we can just pretend that there's kind of like a tap the person in front of me function going on here, where each person just takes the question down the line until you get to the guy who's at the front of the taco truck. He says, no one's in front of me, I'm at the front of the line. So then the guy behind him is like, oh, okay, so there's one person in front of me. The guy behind him says, oh, okay, so there's two people in front of me. And then they bubble that answer all the way back to you, until finally the guy in front of you says, oh, there's 15 people in front of me. So you can say, oh, cool, great, there's 16 people in front of me. And if that doesn't make sense right now, it's fine. Why you would go all the way to the front to then bubble that answer all the way back. It's a little bit sticky, but you'll see why that happens. That's why the description is the way, you'll see why I chose that metaphor, because it's kind of what happens. But yeah, I digress. Let's maybe get into some of the basics of how recursive functions work so we can better understand that taco analogy. But let's think back on iteration. So what are some of the three key components that we need to make sure that our loop works as expected? Remember, these are the things that we always need in iteration. Who remembers them? Or one of them? You are
We need
muted.
an initial value.
Initial value, beautiful. Jordan.
We need a update condition.
Okay, you got the third one?
Anyone else wanna answer the last one? I forgot it. Yeah, you can.
All good.
You can try. Yeah.
That's okay. You're 2 for
What
3.
else?
That's great. Anyone
Oh.
else know what the third one we're missing is?
Yeah.
Daniel, go for it.
Breaking condition.
Perfect. You've been here before. It doesn't count. Just kidding. Great job. Okay. So beautiful. The three things that we always need in iteration are an initial value, a breaking condition, and an update expression. With recursion, we have basically the same needs here. We just have some fancy new names for them. So now we have our base case, our recursive case, and initial value stays the same because it's just an initial value. But what are these? A base case is simply a problem that can be answered directly. It is the smallest instance of a problem that we are currently working on. It is something that we know. So if we think back to our taco truck, the guy at the front of the line with 0 people in front of them, that is a very easy answer. He says, no one is in front of me, I'm first in line. Or if we think back to some naturals, what is the smallest possible instance of the problem? It's 1, because 1 is the smallest natural number. So we figure out what is the smallest instance of a problem that we can possibly get to, and then we kind of work backwards from that, using that smallest instance as our breaking condition. So we say, as soon as you get to the front of the line, stop tapping shoulders. You're there. You don't need to tap anyone in front of you. There's no one to tap. You're at the front of the line. Same thing. You can think of a base case, again, as being the easiest thing that we are going to do. So the person who's 15th in line at the taco truck might not know that they're 15th in line, but the guy at the front knows he's first. So we work our way down to 1 to figure out how to go backwards from there. Sometimes you might have more than one base case, and that's okay. So in our example, 1 is the base case because that is the smallest natural number that we have. But what if someone goofs and they don't input a number at all? They put in a string. It's perfectly fine to just have some kind of exit condition that will just immediately take you out of the function if there's an improper input. You can also have 2 or more recursive cases. So a popular recursion problem is something like a character counter. So given a word, how many times does the letter S crop up in it? You would need a case for what happens whenever you encounter an S, probably some kind of, increment happening to that counter. And you would need a recursive case for what happens whenever the current character isn't an S. So we don't increment the counter, but we do have to keep moving and keep iterating. So 2 cases, 1 problem. The recursive case has a slightly different job, which is a bit more difficult than just an update expression. Its job is to get us closer to the base case by breaking down the problem. So it's kind of an all-in-one, like it is still being an update expression. It is still getting us closer to that base case, but it's also calling the function. So its job is a little bit more important than just updating an expression. So base case is responsible for returning the small case of the problem, n being 1, anything greater than n. The recursive case sounds like its job is to generate the result by adding n, by adding to n, by subtracting from n, sorry. Let me restart that sentence, that was bad. So the base case's job is to exit us out of the function. It tells us when we've gotten to our smallest known quantity. The recursive case's job is getting us down to that smallest case. So we recurse until we hit our base case, which is our breaking condition, and then we can return those values back up through the line and figure out where we're at in the taco truck. Yeah, Carolina.
Yeah, thank you. So I'm trying to make sense of the base case. So I think, and correct me if I'm wrong, but I think you gave an example of, let's say there is a string and you have to kind of count the numbers of the X. So in this case, because you're saying that the base case is trying to find like, it's probably not what the words that you use, but like the smallest case that will get us out of the recursion. So in this case of the finding the S on a given string, the base case will be where if there are no S, return something. That would be like the base case, because that's what I'm struggling with. Like when I read a problem, I'm like, okay, what would be the simplest? Or like,
no worries. Character counter. The base case is actually not going to be looking for whenever you find. So let's say the word is cuppy. I am looking for peas. So how many times does the letter P appear in the word cuppy? My base case isn't going to be find a P and then return, because there's 2 P's in here. If I returned, I would miss one of my P's. So the base case is actually going to be something more like,
I figured, and so that's a great example. So I figured that the base case will be like, if the word is not there, or that doesn't even make sense because that's what you're looking for. I'm sorry, I'm just trying to make sense of like the base case and how it works.
Close to what the base case would be. You're so close. So I will let you keep thinking on that. While I talk about the recursive case. Like I said, this is going to need 2 recursive cases. So recursive case 2, recursive case 1. I find a P, recursive case 2. I don't find a P. And then when do I want to stop looking for letters? What do you think would be like the easiest way to tell I'm done searching a word?
I will figure it by the length of the string, but I'm not sure.
That's exactly right. As soon as I run out of string, return. Don't keep running for forever. As soon as we're done looking at the word that I was given, return. So I run out of letters to iterate through. Does that make sense?
Thanks. That's helpful. Thank you so much.
So like the first time we run through, we have I at 0, C, U, P, P, Y. We don't find any matches. The next time we run through C, U, P, P, Y, we still don't have any matches. We have to keep going, and so on and so forth. Ooh, guess what? We found a P in this iteration. That's pretty fun. So our counter increments. Next time we run through, oop, yeah, I think that's right. The same thing happens. Our counter increments. Very exciting for us. And then the final time, boop, 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 nothing. And then we run out of string, so we want to return. So does that make sense? Cool. Sorry about losing you all. Hopefully we're good now. Okay. Let's actually see something in practice now. So let's kick it up a notch and see what some actual recursion looks like. So who wants to take a stab at walking us through this first recursion? Gail, jumping for it. Go for it.
Okay. So we've got our global memory call stack set up already, and our local memory, or global memory, sorry. So we'll declare a function, sum naturals, and store its function definition in global memory.
Okay.
And then we'll declare a constant variable output and assign its value to the evaluated result of sum naturals by passing in the argument 3.
Okay. And that stays undefined until we dive into the weeds and figure out what this evaluates to. So what happens whenever we see this function get invoked?
We open up a local execution context, and we pair our arguments with our parameters. So in global memory, n will equal 3.
In local memory,
local memory, n will equal 3.
Okay.
And then we have a conditional statement within our function block. So our condition is if n is less than or equal to 0, we will return 0. And
is this true? Is 3 less than or equal to 0?
yes. So because
is it?
Oh, sorry. I was thinking greater than. No, it's not. So we won't return 0. And then, so we'll go on to our else condition, which is that we'll return n, which is 3 plus some naturals with the argument n minus 1. So we're invoking some naturals again within the function. So we will return the evaluated result of n plus the evaluated result of some naturals with the arguments n minus 1. It's a lot.
It is a lot. You're doing great though.
Okay.
We forgot to put this on the call stack. So sumNat3 goes on there. And then this looks a little bit different than what we were previously doing. Here we have the call site. Do you have any idea what the call site might be referring to?
No.
This is just where was the function called. So up here, it makes a lot of sense because this just happens in global. That's not very scary or, crazy. But then inside of here, this is the same function getting called from inside the function. So we kind of we need to keep track of where functions are being called from. So for this first instance, the call site is just going to be global, not so bad, not so scary. But now we have to go in, and this can't just be left hanging as undefined. We have to actually go in and evaluate what this result is. So we've seen a function get invoked. We saw the function definition or the function label with parentheses after it. That means it's runtime. We have to go ahead and execute this function here, sumNat on the argument 2. So let me steal another little execution context for myself, and you tell me what happens as we try to evaluate.
Yeah, so sorry, can you scroll up a little bit?
Yes.
Okay, so we'll pair our arguments with our parameters again in the local execution context 2, sumNat 2. So n equals 3. Or sorry, 2. No, wait, because n equals 3, but n minus 1 is 2.
Yes. So this is the function that got called, the sumNat. So you said we take sumNat n minus 1, which is just sumNat of 2. So we are now trying to evaluate what is sumNat 2. So we enter this new active execution context to try and figure out what is sumnaturals of 2. And this is coming from the call site of sum.
Sorry, I think I just got lost.
No, you're all good. You're doing fine.
Can you scroll up a little bit? Or,
of course. Let me.
Okay.
Yeah. How's that?
That's better.
Okay. Doing great. Keep going.
So if n equals 2, are we just adding 3 plus 2 and returning that?
Nope. So we're just going through those same steps that you did here, but this time our new argument is 2. So we have to do our conditional check to see, is n still less than or equal to 0?
Oh, okay.
So we're just running through it again the same way we did sumNat 3.
Okay. So 2 is not less than or equal to 0. So we won't return 0. We will go to our else condition. And we will return 2 plus some naturals, the evaluated result of some naturals with the arguments n minus 1.
And what does n minus 1 evaluate to?
1.
1. Beautiful. Okay, so once again, we have found ourselves with a return statement that is invoking a function that we have to go evaluate before we can do any of this addition. So we still can't come back and figure this out. This is still left hanging. And now we have another function that is left hanging. So we have to evaluate what sum nat 1 is now. Nope, not that. There we go. Okay, now our active execution context is going to be sum nat 1. So we're trying to figure out what the result of sum nat 1 is, and it was called from within sum nat 2. This gets added to the call stack as well. Okay, so same thing as what we did here in sum nat 2 and sum nat 3. We just run through the whole function again, the whole diagramming again, this time matching this new argument with our old parameter. So do you want to take it away?
Yeah, so if n, which is in this case 1, is less than or equal to 0, we will return 0. Because it's 1, it's greater than 0, so we won't do that. We will go to our else condition, where we will return 1 plus the evaluated result of some naturals, passing in the arguments n minus 1.
Which is?
So, yeah.
Okay, so once again, we have to run through the whole rigmarole of adding it to the call stack. Sum nat 0. That gets pushed onto the call stack. We enter the active execution context to figure out what sum nat 0 is. Let me actually write that there. So it's 1 plus currently undefined, but we're working on it. Up here, our active context is sum nat on 0, and the call site was nat 1. Okay, what happens in this run through?
Can you scroll back up to the?
Yes, I apologize. This is
no worries. So because our if condition is less than or equal to 0, it's equal to 0. So we will return 0.
Okay, so we pair our 0 with our input argument of 0 with our parameter of n, and then we check, is 0 less than or equal to 0? Yes, it is, it's 0. So in this case, we are going to return 0 as the base case said, return 0. Okay, so cool. Finally, we don't have something unresolved in our return statement. We have an actual value. That return value is 0. Where does this value get returned to, do you think?
Global memory. Oh no, sorry, it's the taco line. So it goes back to sum nat 1, and then sum nat 1 returns it back. Is that the deal? Yeah.
Exactly right. So we have a return value. This gets plugged in right here. The guy at the front of the taco truck turns around and says, it's me. There's no one in front of me. Exactly right. So we are able to knock this bad boy off the call stack. We have our return value and it gets plugged in here. Okay, and then the same thing happens here. Now we have a return value. What is the 1 plus 0? It's 1. So this is now our new return value. From this context, we are able to garbage collect this off the call stack and return that value here. Okay. Keep going. What happens now that we have this return value of 1?
Wouldn't it just keep going back so that we'd have,
exactly.
I guess I don't know what the return value would be for sum nat 2. Is it still just 1 again, or are we?
That's okay. Let's figure it out. So we have a return value, and where are we putting this return value? Where it was called. So we look at the call site, see sum nat 2, see where we need to plug in this value. It's just a 1. And then from this function, sum nat 2, we return 3. So return value from sum nat 2 gets returned to sum nat 3. And then once we have that value, we're able to pop that off the call stack. And I apologize, my arrows look stupid. Okay, so we have this return value of 3 from sum nat 2, it was called inside of sumnat3. So we need to plug this 3 in somewhere. Where do we go?
We'd go to our return function and add that to 3, so it'd be 6.
Okay. So our return value is 6. And then where are we returning this 6 to? We'd look at the call site to figure that out.
Can you scroll up again?
Yes.
So yeah, so global memory.
Global memory, it is now taking the place of this kind of left hanging evaluation here. Now we know that whenever you invoke some naturals with an argument of 3, you get a return value of 6. So output is just 6, and this gets popped off, and then all of that gets garbage collected. As we were going, all of these were getting garbage collected. I just didn't want to put lines through it. The line work in this is not great. That was beautiful, Gail. Really well done. Really, really well done. Let's take some questions. SQ, I noticed your hand go up a while ago, but I didn't want to stop Gail. So what is going on? Hopefully you remember.
So what did you say the call site was? Was it just like the text, the call stack? Like it keeps, I mean, I know what it is in my head, but I can't explain it the way you did. So can you please kind of reiterate how you said what the call site was?
Call site, exactly. Yeah. Okay. So where you see the function get invoked from, that is the call site. So some naturals of 3 is invoked inside of global, because this is just, that's where we put all of our global memory things. We're just like, this is just the random outermost level of the file that we are running through. So we have our some naturals in there, we have output out there. Some naturals with the argument of 3 gets invoked from this global space. So its call site is global. Some naturals of 2, on the other hand, is being invoked from within some naturals of 3. So its call site becomes sumnat3. Does that make sense?
I'll figure it out. Thank you so much.
No. So if we were to plug these in, if this becomes sumnat3, doop, then that means that this call here is sumnat2. So the call to some naturals of 2 it's coming from inside the house. It's coming from inside some naturals 3. So this function, sumnat3, was called in global out here, but then whenever we actually go inside of some naturals 3, we have another function being called.
Yeah.
That's sumnat3. Sorry.
Yeah. So sorry. No. I get that. I guess I was kind of looking at it from the call stacks perspective, like. Is call stack, is the call site just using the call stack? Like essentially it's what it's using, right? Like when you put the function there, like your call, that's what your current call site is, or the one before it?
Yeah, kind of. That's a good way to think about it. It's just a little bit more helpful to see explicitly where the function is being called, like recursive exercises, but you're correct. It's just what's getting thrown onto the stack.
Okay. All right. Well, thank you so much.
Of course. Cool. Alana, what's up?
Yeah. Could you explain the taco line metaphor one more time?
Yes. Okay. So I am hungry. I want a taco. I come up to a line, but there's like a bunch of people in front of me. I don't exactly know how many people there are though. So I'm back here at the end of the line, and I tap the shoulder of the person in front of me to say, hey, how many people are in front of you? They say, I don't know. I have to evaluate that still. So they push it along to the next person. They say, hey, how many people are in front of you? Well, I don't know. I have to evaluate that. Hey, how many people are in front of you? No people. We hit the base case. I'm at the front of the line. We can return. So they say there's 0 people in front of me. And then they take that back to the guy behind them who says, oh, there's 0 people in front of you. That means there's 1 person in front of me. And then the guy behind him says, oh, that means there's 2 people in front of me. So you kind of like bubble that return value from down here all the way back to the start of the line, where I can say, oh, cool, there's 15 people in front of me. Does that make sense?
That's really helpful. Thank you.
Of course. Yeah, I feel like I always heard people say like the value bubbles back up, and I never quite knew what they were talking about. So hopefully this is helpful and it's clear. And if it's not, someone stop me. Someone ask for more clarification, because I will move on. Yes. Okay, perfect. John, what's up?
Hey, you You mentioned that, well, this is just like a little, I guess, a question about why are you using invoke versus calling? Like, what's the difference between calling a function and invoking it?
Bad technical communication, use invoke. That's the difference. A function being called is just like, layman's terms for a function being invoked. Sorry, I'm not always the best at keeping the tech. Is that clear though? I'll try and use invoked from now on.
So I just feel like, okay, well, I just feel like it just I would use invoke in a technical interview, basically, is what you're saying, versus I feel like if I'm at work, I'm gonna be saying calling a function because it's just clearer. But
yeah.
Okay.
If you don't get hired because you said call the function instead of invoked a function, that company's not fun. Don't work there. So, like technical communication, it's important in the sense that like we have to make sure that other engineers can understand what you're saying. So like, do you understand what I'm saying whenever I say calls versus invoked? Most people would say yes, but you're right. For the purposes of getting you ready for the technical interview where you're specifically being like graded on that, if you wanted to be precise, you would say a function being invoked. But like call stack comes from functions being called. So like it's like a case for like the colloquialization winning out type of thing. Like invoked is technically correct. Call is everyone's going to understand what you're saying. So don't be too hung up on that. I can't imagine someone not giving you a job or not letting you into a program because you said call the function instead of invoke the function. But yeah, good looking out. Gail, what's going on?
I think somebody mentioned this in the chat and you might have already kind of covered it or maybe you will, but I'm just curious, like this seems like the kind of thing you could do with like a loop, maybe. What's like the advantage to recursion as opposed to a loop?
So it's more declarative to use recursion, but you're absolutely right. Recursion is just another way of doing a loop. So it's kind of circular thinking. It can be used to do other things, but the most like base comparison between recursion and a loop, they're doing the same thing. They're both ways to do the same thing. So if, say, someone were to give you like the stipulation in an interview where you can't use any methods or loops, you could use recursion to solve a problem. So it's kind of like sometimes people might handicap you by saying you can't use a loop. So recursion is the way to go.
Is there like a processing advantage or like anything like that?
Yep. So it's technically you save some space and some time by using recursion. It's just a lot more declarative. Adding things to the call stack gets like kind of there's some like pecking order and some priority of how code happens once things have been added to the call stack that you don't see in a loop. So remember we said like if your loop doesn't have a good breaking condition, you have an infinite loop. That is far less. I mean, I guess they're both bad, but like that is not quite as dire as like having a stack overflow.
Got it. Okay, cool. Thank you.
Okay, cool. Rain, what's up?
Okay, I'm just trying to wrap my head because once we kind of like went backwards, like back up the taco line, then I like lost what happened when we went down in the first place. So just one more time, going with the call site, we got that from the call stack, right? Like when I was looking in the like local execution, just seeing that call site, we get that from this call stack, correct? Like when we're going down.
So right, I would have some like function taco that takes in some number. And then obviously like at the time that you were like calling the function, you kind of know, but like that's not the point of the algorithm. The point of the algorithm is to count down from whatever number I input. So we have some logic in here where we would have like say our base case and our recursive case here. Okay. And then we would do some kind of like, I don't know, console.log taco on, let's say I'm the 15th person in line. So what would our base case be in the case of the taco? When do we stop tapping people?
At zero?
Exactly. Whenever we run out of people.
Yeah.
To tap, i.e. 0. There's no one in front of you, you don't tap them. I can't spell anything, and this is an underlying thing. So hopefully that's all correct. What was our recursive case?
No, my brain has stopped.
All good. If there's someone in front of me, if someone is in front of me, tap them. And all that means is just n-1.
Got it, yeah.
So base case, so if n is strictly equal to 0, return 0. Otherwise, else, return n plus the invocation of taco on n-1. Does that make sense? How's that for you?
Yeah.
It's a little bit clunky, the actual like transforming from like, diagramming is all well and good, but how do you actually write this code to begin with? It kind of gets a little funky, but hopefully that's a little bit clearer and helps you see like all we're doing instead of like random, n plus this, it's just going to be -1 every time. So like, because there's only like, it's not a person in front of you. It's not like you're going to have like 2 people in the same place in line in front of you. But yeah, you would just keep tapping n-1, keep tapping n-1. Oh, we're at 0, then bubble it back up. How's that?
Yeah, that's helpful. Thank you.
Okay, beautiful. Rodrigo, question.
Yeah. So when you say that the code is more declarative, I mean, I understand conceptually that it's telling the computer what to do instead of how to do it. But is that synonymous with clean code? Is that just a more technical way of saying just cleaner?
Well, so a very imperative way of telling someone something to do, like if I were to tell you to make like a peanut butter and jelly sandwich in an imperative way, you would have to go through each and every single step where you would say like, take a bread bag, untwist the twist tie, twist the bread open, take out a slice, put it in the toaster. You have to like list out what each step is doing. Whereas declaratively, you just say, take out piece of bread, put on peanut butter. Like you can kind of like, it's not quite as esoteric in the details. You don't have to list everything out. You can just straight up say, if it's 0, return 0, otherwise return this. You don't have to go through like, while n is less than this, keep doing this check. And then while that happens, update my results, then add something to it, then add n to the result. Like it's just a little bit more declarative. Is this cleaner code? That is up to the interpretation of whoever is reading the code. So like in coding and software engineering, you were typically never working in isolation. There was always someone who is going to be having to review your code, review your PR, all of that stuff. So it is important that not just you are able to read it. If your coworkers don't like recursion, don't like this kind of more declarative code. I mean, I don't know. Declarative isn't necessarily synonymous with recursion, but like if you are working with people who are more comfortable with loops and reading loops is better for them, use loops. Those like fancy code wars algos where they solve things in like 1-line answers with like complete gibberish titles. That's great for them. I don't know what they're doing. I wouldn't approve that PR. I would make them spell out for me exactly what is happening. So like the entire point of engineering is to be as clear and as precise as possible for whoever comes after you and is reading that code. So kind of just like workplace, environment. If they're cool with you doing a little fancy recursion, that's fine. If they don't like that, rewrite it as a loop. Easy peasy. Is that cool? Alvin.
Hi. So I had more or less the same question, but you also mentioned the call stack when you were the first time you were saying recursion makes things more declarative. How can you elaborate a little more on how the interaction with the call stack would make recursion more or less favorable in a certain situation?
I don't know that they would. it really depends on the use case. You would never consider like, oh, if I wanted to optimize my call stack, then I would use recursion here instead of using a loop here. I don't think that you would ever think about it like that unless you were like truly like a part of a startup's infrastructure team and you were trying to like set things up as best that you possibly can. I don't think that it would all happen so quickly. You probably wouldn't even consider which would be more time or space efficient. But like if I just had all of this happening in a loop like I did over here, it's only getting added to the call stack once. So like if this execution fails and gets hung up for whatever reason, then we're just kind of stuck there. But if I have all of these different stack frames to go through, I guess, like, I don't know, if you have an infinite loop, I don't know. I wouldn't really concern yourself with how the call stack makes it more efficient to use recursion. Maybe I said something incorrect earlier because I don't think that that is super important. That's a not great answer for that, Alvin. But,
No, I appreciate the extra info. Thank you.
yeah, I truly don't think that, personally, I don't think that that is super important to make of a distinction. Jose, what's going on?
Yeah. So I don't know if my conclusion is totally right, but comparing the iterative paradigm and the recursive paradigm, I will say like the base case is equivalent to the breaking condition. Correct. And my recursive case is equivalent to my updating condition. So that's the way I kind of see it, in like putting both of them in perspective. I don't know if it is completely right or not.
It's absolutely correct. I think if we go back to this slide where we have the three things for imperative or for like using a loop, it's your initial, your breaking, your update. And then if we skip ahead to recursion, we have base case, just like you said, takes the place of our breaking condition. Recursive case takes the place of our update expression. Initial value stays the same. So that's a great way to think about it. You're dead on.
Thanks. Yeah.
James, what's going on?
Thank you for taking my question. Are we kind of at the end? I have a question for the end. I don't want to derail us. Do you have more to lecture on, or?
We're not even close to the end. Just ask a question.
Cool. Okay, you're stopping. I'm going to hold off then, because mine's about a specific recursion problem that I was having trouble with. Also, I had watched a YouTube video recently about recursion in JavaScript and recursion in other languages. I think Alvin had that question before, and it had mentioned JavaScript being kind of inefficient for recursion and other languages like Scala being better for stuff like that. I don't know if that was, correct me if I'm wrong, but that was just something I saw in a different recursion lecture, and maybe that was useful, but yeah.
That is a good point. So because JavaScript is single threaded, like if something breaks in the call stack, that's the only call stack we have. Other languages with multiple threads have multiple call stacks. So they're not quite as like crisis mode if something goes wrong. But Scala is the worst. Don't tell them I said that.
Yeah, fair enough.
There's something really fun in Scala. Like there's this like framework that's called like Cats.io that I thought would be so fun and cute. It's disgusting. I hate it. Okay. Felipe, what's up?
Yes, I wanted to ask you, would you say usually recursion is better for time and space complexity, or it's not? Because if you say that it's not widely used, then I guess it's not better, right?
So again, it's like an algo bro world thing where like if you are super concerned with having the most time complex, like the best, the fastest algorithm you could possibly have, then like maybe you would consider that. But like I haven't heard anyone. So the way that in programming you would differentiate the different speeds at which algorithms process is called big O notation. So like you would not really hear like, I don't hear people going around the water cooler being like, oh, my function was O of n, and someone being like, oh, it wasn't logarithmic, you should refactor that. Like you just don't hear things like that unless you are like, again, in an infrastructure role where you are trying to make the site. Like I don't know.
Or maybe for interviews, right? It's good to like show that maybe you could do it in some way, but for this time you will try to do it in a big O n equal
I don't remember how was it, right? But
Yep. If you wanted like fancy buzzwords, yes, you would say things like that. If you were just talking to another human being, you probably would not. But yeah, that's a great point. You do have to still get through the interviews. So like it is helpful to know these kinds of things. I certainly don't know them super well. So it doesn't like, again, if you not getting a job happens because you didn't know the difference between logarithmic and exponential big O notation, I don't think that's a very fun place to work. But that's just my personal opinion. That does not have to be your opinion, and that is totally fine.
Okay, thank you so much.
Of course, Hank.
So with regards to the technical interview, I know you're saying, well, I'm just thinking about what you were just saying about like job interviews. Obviously you kind of want like a cool, sleek way of like problem solving for whatever problems you're doing. But we're probably being tested on knowing everything, right? So if there is, for example, a problem that we're given, and I haven't really yet taken a look at what the interview questions are like, but if you had a question where like it seems like they're setting you up to try to use like a for loop to answer it, or like use, I don't know, maybe like callbacks in some way, or maybe a reduce situation. Like I feel like there might be situations where you could use reduce instead of recursion. Would you say that it would be like bad to use a recursive solution if you feel like they're trying to point you towards reduce or something more like that?
No, it wouldn't be bad. It's truly like a choose your own adventure, whatever you were comfortable with, whatever helps you get to the end answer. If your interviewer, for whatever reason, like if you start doing something a recursive approach and they're like, no, maybe you should do a loop. Like if someone explicitly tells you something, then it's probably like, it's always a good idea to just listen to what the interviewer is telling you to like show, I follow directions. I can take hints from people, but like, there's no like moralized, like it's not worse to do one thing or another in an interview. There's like potentially specific buzzwords to like look out for where they're like a function that invokes another function. Like maybe that's your clue, but like, oh, that's probably a callback. It's a function calling a function calling itself. Oh, that's probably a recursive. Like, there's like keywords that you can hear in like prompts. But it's truly like, we're engineers. We can do anything. We can solve anything 5 different ways. They're all totally valid. Some of them are probably faster, but unless you want to like truly get into the nitty gritty of that, you don't have to worry about it. Sometimes it's even better to solve something in the slowest way possible so that then you can show off at the end and be like, oh, but I could have refactored it to be faster by, instead of using a nested for loop, by doing it this way, by using reduce, and then you can look fancy and impressive and you didn't even have to solve it the hard way.
Yeah. So. Reduce in particular, for me personally, I don't know about everyone else, like that is actually the one concept that I'm still struggling with, I feel. So I can't really tell how important that is to the interview, especially when there's like ways to work around it using recursion or something.
I'm going to level with you. It has been a very long time since I did the interview, and I don't like, my day job is not with Codesmith doing interviews. So I don't actually know what's on the interview anymore at this point. I have truly no idea how much or how little reduce appears on it. So that's not very comforting, but I know reduce is a white whale for a lot of people. So maybe someone around in the class would be willing to pair program with you and help you out on figuring that out.
Cool. Thank you.
Okay. Any final questions before we kind of shimmy back into the lecture? Nope. All right, cool. Okay. So the key idea of recursion, again, is to basically ask yourself, how is this problem self-similar? How can I break this down into something that is self-similar but smaller? How can I tap people until I hit 0? How can I subtract from n to get to 0 so I can hit my base case and get out of there? So this is kind of what recursion is all about, breaking the problem down through the process of decomposition, which is just making something smaller and smaller until we get somewhere that we know, our base case, until we're at the front of the taco truck line. So each function passes the buck to another function call until you get to the end of the line. And then finally, all of those results kind of bubble back up to that initial function call. So how do we get the result? What we just looked at is called linear recursion, and that simply means that we have to do some additional work after we get that returned result from the inner function. So remember, we did some evaluating and then we had to wait for a result. We did some evaluating, had to wait to figure out what this is, had to wait, figured it out, brought it back, brought it back, brought it back. All these functions were left hanging until we worked our way all the way down to the chain. That is linear recursion. A stack frame is what is known as the active execution context. It's what we push and pop off of the call stack whenever we invoke functions. Or I guess it's what we push onto the call stack when we invoke something, and it's what we pop off whenever we hit our return statement. So the thing getting pushed and popped is called a call stack or a stack frame. And each time that we invoke a function, we create a new execution context with local memory to save things, and we can return back to where things were called following the stack trace or following the call sites. So this information is all saved in what sits on the call stack. So as we walk through this code, we're going to pay attention. Oh, we already did that. We already walked through the code, so we don't need to worry so much about that anymore. We already saw how that works. So wouldn't it be fun if we saw it work in a completely different way now? Ooh, I wonder what that means. Okay, same basic function. We are trying to sum up all natural numbers, but now it looks a little bit different. Who can see some, right off the bat, glaringly different things about this way of writing the function? Rodrigo.
We're using a default value or result.
One more time.
Default parameter.
Yes, beautiful. We're using a default parameter up here. And can you explain to me what a default parameter is, maybe?
Yeah, definitely. So the default parameter is a parameter that is set up in such a way that the first, if no argument is passed in for that parameter, then it assumes that the default value, which in this case, the default parameter would be result, and it's assigned the default value of 0.
That was beautifully said. So default parameter, that just means, like he said, we have this parameter up here where if we don't pass any argument in for it whenever we call the function, so like here you see a call for some naturals, n is 3, but we don't have any value in here for result. That just means result is going to default to 0. But later on, whenever we call some naturals here, we see that result is actually quantified inside of the function call. So it's no longer a default parameter. Now, instead of 0, or result is whatever this evaluates to. Okay, cool. That is one thing that is different. Another thing that's different is simply the fact that we have 2 parameters. That's kind of fun, kind of exciting. Does anyone see a reason why we would want to kind of quantify this result equals 0? Why wouldn't we just have result equals 0? Here's the first line in the function. Yeah, go for it.
Because then the only line of code you need is just the recursive calls and then the result, well, and the if statement.
Sure. So if result was here, like if there was a line in between the name of the function, this if statement that said let result equal 0, then every time some naturals gets called again, result would get reset back to 0, get reset back to whatever this is. We also can't like keep it as a live value that we are working with. We can't update it. It would just go reset to whatever we declared it as each time the function is called. So default parameters, pretty fun, pretty cool. Let us do some fun things. But anyway, this is opposed to the linear recursion that we just saw. We would call this tail call recursion. It's a little bit different because on the recursive line, the only thing that is happening is a function call. There's no funny math business. There's no 3 plus the evaluated result of some naturals. It is just straight up a function call. This lets us do something pretty fun with our call stack that I will show you in a second, but just bear in mind, not all browsers will let you do that fun thing that I'm about to show you. So it's not too exciting, you know, engineers can never agree on anything. So not all of the browsers allow it. Okay, who would like to walk us through this one? Rodrigo, he's on a roll. Let's do it.
Yeah, sure. So the first thing we do is we declare in global memory the function SumNaturals. So we declare the function SumNaturals and we store the label and the function definition in global memory.
Okay.
And then the next thing we do is we declare a constant output and we assign to it the evaluated result of invoking the SumNaturals function with an argument of 3.
Okay, perfect. And what happens as soon as we see a function has been invoked? What a chain of events kicks off?
So we push that call to the SumNaturals function to the call stack.
Okay.
And we set up a local execution context. Someone in the chat said that the toe entered a new local execution context, but
I'm gonna find whoever said it. I'm gonna tell them not to let you in. Hank, awful to the shadow realm. Okay, so the toe has entered the thread of execution has entered SumNaturals, passing in 3. So what happens now? What is our call site in this instance?
our call site would be global because the function was invoked in the global execution context.
Beautiful. Okay, so what is our first step? Now that we are inside of our function's local execution context, what is our first step?
Yeah, so the first thing we do is we declare a local variable n and we assign to it the argument 3. I'm not sure that's the exact way to do it, but basically since we're passing the argument 3 for the parameter n, then we assign to n the value of 3 in local memory.
Okay. What else do we?
Now we have a default parameter.
Mm-hmm.
And since no argument was passed in to the first call to SumNaturals in the global execution context, then result, we're assigning to it the value of 0.
Okay, that's fun. All right, so now we have this next line of code, this conditional check. So what's going on inside of that?
So there, the first thing we're doing is, and it's a little, well, here, sorry.
Yeah, I know. Hold on, let me zoom in here.
Thank you. Yeah, so the first thing we're doing is we enter the if statement, and there we're checking if n is less than or equal to 0. Right, and the value of n that we have in local memory is 3. 3 is not less than or equal to 0, and therefore that evaluates to false, and then we enter the else so we don't return result. Instead, we're returning SumNaturals. We're returning the evaluated result of invoking the SumNaturals function on n-1 and result plus n.
Okay, so what's n-1?
Yep. So n-1, so n is 3 in global memory, 3 minus 1 is 2. So 2 and result plus n, which is 3.
Okay, 0 plus 3 is 3.
Yes.
n-1, 3 minus 1 is 2. Perfect. Okay. So this is where something a little bit interesting happens, because we actually have a return value right here and now. The return value is SumNat23. So we are able to just straight up return this. So this is actually going to be returned here. So our output is now actually, oh, we still don't know what it is, but technically this time it's coming from some nat 2, 3 instead of before where it came from some nat 3. That's a little arbitrary, maybe a little bit confusing, but just know like we hit a return value. So technically we could garbage collect this. We could just replace this stack frame since this is just straight up a function being called. But we're not going to, maybe we're not going to do that just yet. We'll just run through this like it were a normal problem. So we have a new function being invoked. What happens whenever we see a function get invoked?
So we push the call to the call stack.
Exactly. Some nat 2, 3 gets pushed to the call stack. Beautiful.
And we create a new execution context.
Okay. What is our call site for this function?
The call site in this case is some nat 3.
Beautiful. So the call site is still keeping track of where this function came from, even though technically we could garbage collect this entire stack and just have this take place. But again, that's getting into the weeds. We'll talk about that after the fact. I'll let Rodrigo keep going.
Okay. And so the next thing that happens, so we push to the call stack and we create a new execution context. The first thing we do is we declare in local memory the n, and we're assigning to it the value of 2.
Okay.
And then we're also assigning to result the value of 3.
Okay, beautiful.
Local.
Now what happens?
Then the next thing that happens is we check to see, so we enter the if statement, and the condition evaluates whether or not n is less than or equal to 0, n is equal to 2. So 2 is not less than or equal to 0. That evaluates to false.
Okay.
Therefore, we enter the recursive case, which is to return the evaluated result of invoking the sumNaturals function on n minus 1. Which is n is currently 2. 2 minus 1 is 1. So we're invoking sumNaturals on 1. And the sum of result and n. And result in local memory is 3. And the n in local memory is 2. 3 plus 2 is 5. And so we're invoking sumNat on 1 and 5.
Beautiful. And since we have a return statement with a function call, the return value is just that function call. So sum nat 1, 5 is our return value. So we can pop this guy off. We're done. We hit a return out of our function. We don't have to do any further evaluating. We're technically done. So we can just pop that bad boy right off the call stack. But again, we're not going to do that just yet. We're going to add another frame. Sorry, Rodrigo. You can tell us what happens next as I get that up.
So the next thing that would happen after we push sumNat, the call to sumNat on the arguments 1 and 5 to the call stack would be to create a new local execution context with its own local memory. And within that local memory, we would assign to the two parameters n and result the values of, I believe, the values of 1 and 5.
Okay. What's the call site for this?
The call site for this is sumNat of 2 comma 3.
2, 3. Yep.
Okay.
2, 3. Nope. Okay. So what happens now inside of here? I know you can't see the code anymore. I'm sorry, but
that's okay. So next thing we do is we enter an if statement, and we're checking to see if the condition of the if statement is met. And I can't see the if statement, but I believe it was n is less than or equal to 0, and 1 is not less than or equal to 0, and so it evaluates to false.
Okay.
And therefore we enter the recursive case once more.
All right, which is going to be?
Which is we're returning the evaluated result of invoking the sum naturals function on n-1, comma, result plus n in the local memory of our current execution context is 1. So 1 minus 1 is 0. So we're invoking sum1 on 0. And I believe that result is result plus n. Right, so result in local memory is 5, n in local memory is 1. So 5 plus 1 is 6.
Okay.
So we're invoking sum nat on 0, 6.
All right, cool. So we have a return value of sum nat 0, 6. We see a function getting invoked. So what happens?
So we push the invocation to the sum nat function on 0 and 6 to the call stack, and we create a new local execution context.
Beautiful. And the call site is?
The call site is sum nat 1, 5.
Beautiful. All right. Let's pair those params and arguments.
Yes. So we're assigning to the value of our parameters n and result. To the value to the parameter n, we're assigning the number 0, the value of the number 0. And to the parameter result, we're assigning the value of the number 6.
Okay. Something fun's going to happen now in our conditional check.
Yes, and here, well, we enter the if statement and we're checking if n is less than or equal to 0. 0 is indeed equal to 0, and so it evaluates to true. And now we are returning the value of result in our local memory, which is 6.
Okay. So we return 6. All right, interesting. What happens now?
Well, now, since, as you mentioned, because we've been returning in each of our calls, then we don't need to garbage collect any of the past ones. So what basically would happen is that value of 6 would be updated immediately to output. So we update output to the value of 6, and then we pop that last call to some naturals on 0, 6 off the call stack, and now that call stack, that execution context is eligible for garbage collect.
Beautiful. So if we had been being good housekeepers the entire way, we would have popped these as soon as we hit this return statement, we would have popped it off. As soon as we hit this return statement, popped it off. So then, like he said, by the time that we get to this final local execution context where we have our return value that gets pushed to the output, that would get popped off, and then we'd be right back into global. So you can kind of see this is different from what we did before, where we had to keep track, like there were functions left hanging that we had to go back to and resolve before we could exit out of our function. But here we don't have that. We don't have any math or any evaluation happening in this return statement. We just have a function call, which allows us to do something kind of fun, where we could say, we would just have a global. And then we could just kind of make a little stack frame for all of these different function calls. So we could have a sum nat 3, and we could have a function call, or like a call stack frame for sum nat of 2,3. And then whenever this gets invoked, we could just push this. Oh, it doesn't come together. We could just push all of this onto the call stack, let that evaluate. As soon as we hit that return value of sumnat23, this gets garbage collected, it goes away. We can replace the stack frame with the sumnat 2,3. So with tail call optimized recursion, you don't have this like big, you know, call stack that has a million functions piling up on top of it. You're getting to the evaluation, you are getting to a return statement with each invocation. It is much more memory efficient. Questions on that, anyone? Yeah, SQ, go for it.
Okay, so the example we did before this was linear recursion, right?
Correct.
And so this one is called tail call recursion.
Yep.
And with the call stack, I didn't quite understand, but we could have been just popping it off every time we move to a new local execution context, right?
Correct.
So we just kind of left it up there as like an example so we could kind of see it better. Okay.
Yeah.
Thank you.
But sure. So as we run through this, if it's 0, return the result, but it's not 0. We're going to return this function instead. Oh, okay, cool. There's my return statement. I'm done with this function. As soon as we hit this line, boom, pop it off the call stack, garbage collected. Same thing here. Is it 0? No. Okay, here's our return statement. Pop it off the call stack, garbage collected.
Right.
So,
So
the only
I'm so
Go ahead.
sorry. Sorry.
No, you're fine.
No, I was just saying like, so essentially whenever we get the return value, we just basically garbage collect.
Yep.
Okay.
If we hit a return, we're done with the function. We're getting out of there.
All right. Thank you so much.
Of course. And don't worry about interrupting me. I talk too much. You're fine. Interrupt me. I hear myself entirely too much during these. Andy, question.
Yes, hi Rebecca. I followed everything except for the first thing, so sorry if it's a silly question, but like, why did we start with some nats of 3? I followed everything after that, but I was like, why are we calling some nats of 3 from global context first instead of starting on the first line of the code?
We started with sumnat3 because that's what they gave us. That is what they told us to find. What do you mean by starting at the first line of code?
Oh, I thought we would go from like function, sumnats, and then like, you know, go down top to bottom, but.
Oh, sure. So yeah, okay, I see. So whenever we are going through, we are JavaScript, we are single threaded, we're using our thread of execution to read, we go line by line. So we read this line, that was a terrible line, my God. We read this line, we see, oh, you're giving me a function. It's called sumnaturals. So global memory is going to slurp that up. It's going to say, okay, cool. Whenever you see sumnaturals, just know it's a function. And then JavaScript is going to see like, oh, this and this, these are the function definition. This is where the function starts. This is where the function ends. I don't care about that. I'm just reading names and picking things up from memory. So we are going to actually, once we have said like, oh, function sumnaturals, cool, that's a function, save that definition in global memory, it's going to say, okay, I don't really care about this. We're going to move on. So the thread of execution is actually going to skip straight down to this line as soon as it puts that function definition into memory. And then once we have this output being saved to the evaluated result of actually calling this function, once this function actually gets invoked, that is whenever we care about what actually lives in between the curly brackets. Does that help?
Oh yes, totally does. Sorry, it was basic, but when you explained it, I got it. Yeah, we didn't invoke it until we invoked some nats passing in 3, and then we go into the function and code block and run it. Thank you.
Of course.
I'm sorry,
And
it's just
these are
like a brain freeze moment. Like it's like we already knew, well, not we, but I already knew that from back then. But then I missed like, wait, why are we doing that now? Got it. Thank you.
Totally fine. And we couldn't, if we had tried to do this earlier, we couldn't really do it because these are just placeholder values. N doesn't mean anything to us until we match it with our argument. So that's another reason why we skip out of there, because N and I mean, I guess result equals 0. We know what 0 is, but we can't really do very much if we don't have an N, and we don't get N until later on. Okay, let's pop over to Felipe. What's up?
Yes, Rebecca, I wanted to ask, I think I missed it, but the reason well, we may use a default parameter then, it's not only to make diagramming better, but would you say it saves space on the machine by doing the call stack thing and not having to iterate back? Or does it allow us for more complex functions? Or it just keeps the code drier? Or what would be the reason?
So tail call recursion, this style of recursion would help you save space, but that has nothing to do with the default parameter here.
Okay, but doesn't tail call exist when we call a default parameter?
Not necessarily.
Okay.
So the distinction between linear recursion and tail call, inside of linear recursion, you see this n plus a function call. This right here is some kind of evaluation happening that we have to trace back in a linear fashion. That is what makes it linear. So this evaluation happening outside of the function call on this return line, that's what makes it linear. This return statement just having a function call, that's what makes it tail call, not necessarily the parameter.
Okay, perfect. Thank you.
Yeah, so by moving the math from out here to in here, you have optimized the tail call.
Sweet. Thank you so much.
No worries. Jose, what's going on?
So let me see if I get it right. So every time we hit return, we are just returning that function invocation and assigning it to output variable in global memory.
So it only gets assigned to output, I guess, this first time that it gets called, where it's sum naturals of 3. But because sum naturals of 3, you can follow the call site all the way back to sum nat 3. That return value gets placed there. What you said was good though about this just returning the function call.
Okay, yeah, I get it.
Yep. Okay. Beautiful. John, go for it.
What would happen if you forgot to add a base case in a tail call recursive function?
So again, not all browsers let you do this. So Safari, for example, will let this kind of recursion happen, but all the other ones, like I'm using Firefox runs on a different engine from Safari. It doesn't let this happen. It doesn't let you swap out stacks. It makes you go through all of these and pop them off as it happens. So you don't save yourself from a stack overflow, but like theoretically, it could be better for that. But not all browsers let you do it that way.
So it's still a stack overflow, essentially.
It's still a stack overflow.
Right. Thank you.
Okay, so what you just last said confused me a little bit, but
good.
What I understand about the stack frames is that the call site is always the previous stack frame, right? That's why call site for sum naturals 2, 3 is sum nat 3, is because the stack frame below it would be sum nat 3. Is that right?
Mm-hmm. Correct.
And so what I was going to ask is that technically for each sum nats 2, 3, sum nats 1, 5, technically the call site is global because it would get popped off, and now you're saying it wouldn't get popped off in Firefox?
It still gets popped off. It's just under the hood, what's happening is a little bit different. It's still the function working the same way. It's still just like the reason why we're able to hit this return value whenever output didn't call sum nat 1, 5, it called sum nat 3, is because under the hood, all of these are linked back to each other through the call site. Like the call site isn't, whenever you were like writing a function, you wouldn't really consider what the call site is. Like, remember we did like this taco recursion. I don't really care what the call site is. I just care that we're working our way down. And I know that under the hood, JavaScript is keeping track of the call sites as they are happening. It's just in some browsers, you are able to just reuse the stack. And in others, it still piles them on. Is that
okay? Thank you. I have one more question.
Yeah, go for it.
For default parameters, so each time we're replacing not the whole parameter, but just 0 or the number in the parameter. Is that right?
So if we call this function sum naturals when we just pass in one argument for n, then result is going to default to 0. That's what this line here means. But for example, in sumnat 2.3, we're passing in a value for result. So it doesn't take the value of 0, it takes the value that we pass in of 3.
Okay, thank you.
Cool. And the stack frames, it's all very nuanced and probably not really something you at this point need to be terribly concerned with. So I don't want that to like bog anyone down, but just like it's a cool feature when it works, but it doesn't always work depending on the browser. Tammy, go for it.
Just a quick question about syntax. I'm wondering if you could elaborate on the syntax for these problems. I noticed, for instance, I mean, even in the difference between the tail call and the linear recursive example, there's no else statement. And obviously there's a difference in like placement of curly brackets between recursive functions and if else statements. So just could you elaborate on that a bit?
So when engineers are feeling lazy, they write in higher ES languages or versions than ES5, where you would have to have your if statement coupled with an else statement. So now we're allowed to be lazy and just like have an implied else. So that's all that is. And then having this, like you would see if parentheses, curly brackets, and then you would describe what happened in that if case in between the curly brackets. But you can shorten it to just be these fancy little one-liners in higher versions than ES5. So like ES6, 7, 8, 9. I think we're at 10 now. Who even knows? You're allowed to just do fancier things, but under the hood, there's like still an implied else going on here. So if n is less than or equal to 0, curly bracket, return result, end curly bracket. Else, curly bracket, return sum naturals. It's just faster.
Right, so there's no particular, that would work in other cases too. There's no particular attachment to a recursive.
Yeah, if you had more than one line happening inside of this if block, like if something else had to happen as well, then you wouldn't be able to get away with that. But as long as it's quick little one-liners.
Okay, thank you.
Cool. Besseret? What's up?
Could you just give me the differences between the tail call and the linear recursion again, just so I can get it in my notes right?
Of course. Before I tell you, what do you think the difference is?
I'm thinking linear is when I guess the recursive case is outside of the function definition.
It's still happening inside the function definition. It's
Okay.
all to do with this line here.
Yes.
Let me steal this code. Nope, not that. Hold on. Let me steal this and let you compare them side by side. What do you see that is different about these two return statements?
Well, the tail call one is like the n-1 is happening in the brackets, and the on the linear one it's happening. What is that? I don't even. It's like outside of it. I think. Can't tell if the two there. It's like, oh. I mean, yeah, I don't know.
You're super close. You're right. It has to do with this tricky little n right here, where this tail call one, we have no evaluation. We just say return function call. Whereas over here, we are doing some evaluation plus a function call. Return this plus a function call. So this math happening here, that's what makes it linear, because whenever we say that, then we have some kind of undefined function that at the time that we call this function 3 plus sumnat2, we don't know what the answer to sumnat2 is. We have to go figure that out and then take it back to sumnat3. So we have like this linear line of calls being made that bubble back up. Whereas here we're just straight up, like there's nothing left hanging. There's no evaluation happening before or after the function call. It's just function call.
I see.
So if you had to tell me, nice and neat for notes, what the difference between tail call and linear is.
Let me see if I can get it. To me, it's like with linear, let's see. Wow. If in linear, it's I don't know. Sorry, I'm got the.
You're good.
Yeah.
If linear isn't working for you, how would you define tail call?
Tail call is where you're just returning the function.
Exactly.
Just a function call.
So
Yeah, there's something. There's
linear,
more
you're doing more than just returning
the
function.
Okay, there's
You're
more
doing
happening.
some evaluation. Yeah, exactly. That's the only difference.
Okay, cool.
You got it. You
All right.
got it. You're there.
All right, thank you.
Do you need that one more time while you're writing?
Yes. That'd be great.
Sure. So tail call recursion is just the return of the function call. Linear recursion is some evaluation plus a function call.
Okay, thank you.
Cool. D, what's going on?
Hey, can you hear me?
Yep.
Yeah, I just had a question. So like, if you wanted to keep track of some kind of information, but you still wanted to, I guess, get the benefit memory-wise of doing short tail call recursion. So your options for that, are they basically limited to either passing that information in an argument that you're updating and using a variable in global memory? Is that like the kind of two approaches you could use for that, or?
Yeah, exactly. So you could either like pull something in, like you could say like let name equal D, and then you could have like some function that takes in like, I don't know, something like a number, and then you would have to pair like your well, you wouldn't want to do it in a parameter then. So then later on in the function, I would say like assign employee X with this name, assign employee name with this number. So I could still access like, I'm not coming up with this well on the fly, but you could still access this variable name inside the function from global. So that's one way to do it. Or you could do the same thing, but instead have So yeah, those are your two options. You could either bring something in from global to your function, or you could assign it in the parameter and then never update it, or update it as much as you want.
Just one, sorry.
Yeah, go for it.
Just like a follow-up to that, like say recursively you're affecting kind of the keyword value there. So you're, I don't know, concatenating something to it. That's gonna be able to continuously, I don't know how to say it, but it's like the original thing is going to fall out of scope because you're using tail call recursion, but because you're updating the argument and using the argument immediately, you can keep track of that data. Like you're not just going to have the initial value plus the newest value, you're going to have all the values that were accumulated along the way, if that makes sense.
I guess technically you could set it up however you wanted. You could set it up to do that. You could also just never pass in another parameter for it and the default would stay. So like, it just depends on what you were trying to accomplish.
Okay, perfect. Thanks.
Yep. Okay. Any other questions on tail call recursion, the differences between linear and tail call, or are we cool to move on to our last? I promise it is a doozy, but it is the last diagram of class. So, cool. Hopefully we're feeling okay about those two different examples of recursion that we just went over, linear and tail call. Again, one last time, just to hammer it home, in linear recursion, a function call is not the last operation that is carried out. We do more work on the way down. In tail call recursion, the function call is the last thing that happens. So there are also other types of recursion as well, such as multiple tree recursion, but we're not going to get into that. Instead, we are going to talk about what happens whenever a function is called twice inside of itself. So the classic example of this is Fibonacci. You know, classic Google algorithm question, or I guess it was, it's probably too popular now, but here we have a function that inside of its recursive case is calling itself twice. It's kind of crazy, I know, but we still have native our base case. We have two base cases here, one for a case where if n is equal to 0, one for a case where if n is equal to 1, and we'll see why in a second. Otherwise, we have a recursive case that adds two function invocations. Don't worry, we're going to go through it. It's a little scary, it's a little kooky, but we'll get through it together, I promise. But before we do anything with the code, let's first just talk about what a Fibonacci sequence is. Does anyone know off the top of their head what Fibonacci is?
Well, I know it's a sequence of numbers that the pattern repeats in nature quite a bit, and it's tied to the golden ratio, and the Greeks used it in their architecture, but I don't know the formula of it.
Exactly, golden ratio. Beautiful, perfect. That's exactly what it is. It's this fun little swirly doodad that just shows up in nature everywhere. So this ratio between the different segments of this little swirly doodad, it's just found everywhere. So it's in snails, it's in sunflowers, it's in cauliflower, it's in the spiral galaxies. Mathematicians saw this repeating pattern and they said, oh, there must be a reason why this exists. Let us turn it into numbers. And that is what they did. They figured out a formula for it, because why not turn sunflowers into math? That's kind of fun. So Fibonacci sequence all over nature, you know. Here's what it is if you break it down. It is just a ratio where the sum of the previous two numbers equals the next number in the sequence. So if I were to look at this part of the Fibonacci sequence, I would look at the last two numbers in Fibonacci to figure out what the next one would be, or what made it up. So 2, 1 plus 1, 3, 2 plus 1. 5 is the sum of 3 plus 2. 8 is the sum of 5 plus 3. So what would be next in the Fibonacci sequence following that?
13.
13. Beautiful. What would be next after 13?
21.
4.
Yes. It would be 21. Exactly. 8 plus 13 is 21. And so on and so forth. But if we're thinking in terms of recursion, what is the smallest possible combination of numbers that we can have to make up a sequence? It's 0 and it's 1. So we have a base case set up for if it is 0. We have a base case set up for if it is 1. Otherwise, we are just going to keep breaking these numbers down until we get to either 0 or a 1. How do we get to 0 from 8? We would be able to subtract by 2, and eventually it would become 6, 4, 2, 0. If we had an odd number like 5, how would we get 5 down to 0? We would just subtract 1 from it until it hits 0. So 5, 4, 3, 2, 1, 0. So we set up a case for if n is 0. We set up a case for if n is 1. Otherwise, we just run Fibonacci until we get a number down to either 0 or 1. Does that make sense? I feel like sometimes the logic of how to actually write these functions gets lost whenever you're just spending so much time diagramming. So we have a function called Fibonacci. Let me write this outside of a comment, actually, so we can see it. So we have a function definition being assigned. We declare a function, we call it Fibonacci using the function keyword, and we pass in a parameter of num because we want to figure out what sequence, what number, what place the number is in the sequence of Fibonacci. And we know that the smallest instances of Fibonacci are 0 and 1. So we would set up two base cases to get us down to 0 and 1. So our first base case, who can help me out? What is our first base case? What do we need to see? Jose, go for it.
So is n equals 0? Equal to 0?
And it is equal to 0. Okay, what's our other base case?
If n is equal to 1.
Okay, and why do we care about zeros and ones?
Because they are this minimum numbers in the sequence.
Exactly. Okay, so what might our recursive case be?
So it will be n minus 1 plus n minus 2.
Return the call of fib n minus 1 plus fib n minus 2.
Which
That
are
way-
the previous numbers, the two previous numbers of the current number.
Correct. So we can always be sure whether it's even or it's odd, we are going to get it down to either a 0 or a 1. Oh, hello. I've been joined by my special co-host, Soup. Get out of here, buddy. Okay. So if we were to actually code this out, we would have our little if n strictly equal to 0. Then we would return, what are we returning? Returning 0. And if n is strictly equal to 1, then we would return 1. Otherwise, we are just going to return fib of n minus 1 plus fib of n minus 2. And the logic for this is a little bit funny, but hopefully we got it. And if not, then we'll see it in excruciating detail whenever we go to old Humunga Dunga here, just for like comparison's sake. This is how big the rest of them have been. This is how big Fibonacci is. So everyone strap in. Who would like to walk us through the Fibonacci sequence? Jose, is your hand still up because you want to do it?
I can do it.
Oh, he said no. You don't have to. Would anyone else like to do
No,
it?
I can do it. It's no problem.
It's not so bad. It's a lot of repetition. You'll be okay, I promise. Okay.
Yeah. So
Zooming back.
yeah.
Here you go.
So we get into our code. We declare global function Fibonacci and in global memory, and assign the function definition. Then we go down to and declare a global constant output that is going to be equal to the evaluated result of Fibonacci.
Okay.
We create a new local execution context and pair our argument with our parameter. So n is going to be declared in local memory and is going to be equal to 4.
Okay, beautiful. Let's get this function call onto the call stack. So we called Fibonacci on the argument of 4. That means our active context is Fib4, and our call site is coming from
global.
Okay, beautiful. All the groundwork is laid out. So now we just have to do our checks and then see what we got to return. Go for it.
First base case is n equals 0. So no, n is 4. Then we check if n is equal to 1, and neither it is.
Okay.
So then we returned Fibonacci, and the invocation of Fibonacci is gonna be push to our call stack.
Well, let's just get through with what this return statement even is before worrying about executing them.
Yeah, so it's gonna be 4 minus 1.
Okay.
And plus Fibonacci of 4 minus 2, which is 2.
Okay, beautiful. So just like you said, here we have two functions being invoked. Remember, I read my code the same way I would read like a book in Western society, left to right. So I have to invoke this one first and follow this chain all the way down to the bottom before I can even touch this line of code. So what do you think happens now?
So we're gonna patch Fibonacci of 3 to the call stack.
Fib 3, okay, exactly.
Fib of 2.
Not yet. We can't
Oh yeah,
touch
now
this.
we're gonna evaluate it first. Yes. So we're gonna create a new local execution contest. Active contest is gonna be Fibonacci of 3, and call side is gonna be Fibonacci of 4.
Okay, beautiful.
Then we're gonna declare well, n is gonna be equal to 3, and we check our base cases. 3 if equal to 0, no, and 3 is neither equal to 1. So we're gonna return Fibonacci of 3 minus 1, which is gonna be 2, plus fib of 3 minus 2, which 3 minus 2, which is gonna be 1.
Okay.
Then we
Beautiful.
push fib of 2 to our call stack,
Okay.
and then we create a new local execution contest. Active contest is gonna be Fibonacci of 2.
Okay.
And call side is gonna be fib of 3.
Beautiful. Keep going.
And it's gonna be equal to 2. And we check our base cases. 2 is not equal to 0, and 2 is not equal to 1. Then we return Fibonacci of 2 minus 1, which is gonna be 1.
Okay.
Plus Fibonacci of 2 minus 2, which is gonna be 0.
Okay.
So then we push fib of 1 to the call stack, creating a local execution contest. Active contest is gonna be equal to fib of 1.
Okay.
Call side is gonna be fib of 2.
Okay.
And local n is gonna be equal to 1. And checking our base cases, fib is not n is not equal to 0, but n is equal to 1. So we return 1. And we have our return value.
Aha, finally a return value. Okay, what happens with this return value?
So that return value is gonna be replaced. Okay.
Yep, so
we already know this. Yeah, it's gonna be a garbage collector, and then yeah, it's gonna be 1. We already have that value, and then we're gonna to patch Fibonacci of 0 to the call stack.
Exactly, beautiful.
So we create a new local execution contest.
Okay.
Active contest is gonna be fib of 0.
Okay.
And call side is gonna be fib of 1.
Fib of 1, or did we get
Fib
rid
of-
of fib?
What? No.
So this function fib of 0 is being
Fib of
called.
2. Yeah. Right. Yes.
All good.
So we value, well, n is gonna be equal to 0, and we evaluate our base case. 0 is n is equal to 0, and that's true. So we return 0. Yeah. So we already have our second evaluated result. Yep. So then Fib of 2 is gonna be equal to 1.
Okay, let's
And
get
we are
these guys.
gonna, yes.
All right. Okay.
So then we can go back to fib of 3. We already have the value of fib of 2, which is 1, and the value of fib of 1, which is 1.
Correct, but we can't just reuse this frame because
We have to, yeah, we have to evaluate it all over again.
but we know what it is and it won't take us that long. So fib of 1, the call site is fib 3. And we've seen this before, n is equal to 1. We do our conditional checks.
Correct. 0, that's false. Yes, it's equal to red. 1 is equal to 1 is true.
Okay. So what do we return?
We return 1.
We return 1. Beautiful. See, not so bad. Just a lot of repetition. Oh, I can't move the 1. Whatever. Okay. So
yeah,
this goes on. Oh no, I forgot to put it on. We have to put fib of 1 back on the call stack. Sorry. So we put that on, then we immediately pop it off. And let's see, let me do.
Yes, correct.
Okay.
Then
so we have this valuation now. What's the return value?
Yes, it's gonna be 2.
Okay.
Then we can garbage collect that. And
Return that.
return back to our initial call.
Okay, and let's get this fib of 3 off as well. We're back to fib 4.
Yeah, and we push fib 2 to the call stack again. Create a new local execution counters.
Okay.
Then after counter is gonna be fib of 2, and call side is gonna be fib of 4.
Beautiful.
Yes, so then n is gonna be equal to 2.
Okay.
Well, base cases, 2 is not equal to 0, it's not equal to 1.
Okay.
So we have Fibonacci of 2 minus 1, which is going to be 1, and we have Fibonacci of 2 minus 2, which is going to be 0.
Okay, beautiful. Now we're getting somewhere. So
Yes.
we invoke this one first. What happens?
We create a new local execution counters all over again.
Oh. Okay.
Yeah, so after counters is gonna be fib of 1, and call side is gonna be fib of 2, and it's gonna be equal to 1. Then we evaluate our base case. 1 is not 0, but 1 is equal to 1. That's true. We return 1.
Okay. Return 1. All right.
Garbage collect that.
Garbage collect this. Garbage collect this.
Go back
and
to
then
fib of 2. And now we push fib of 0 to the call stack again.
Okay.
Create a new local execution contest. After this contest is gonna be fib of 0.
Okay.
Goal side is gonna be fib of 2.
Alrighty.
And it's gonna be equal to 0. So n is equal to 0, which is true. We return 0.
Okay.
Yes.
Whew. All right. We have a return.
Yes.
So that gets bubbled back up to here.
Correct. 0.
This Garbaggio. Okay. All right. Now we can
And
evaluate.
that's 1.
Okay.
And we go back to fib of 4, I guess.
Oh, we get fib 2 off of there. And then if you can even make it out all the way down here, fib 4 in global. Okay. So 2 plus
1.
Lovely. And then that becomes our return value.
Correct.
So this can finally
Go
loop.
back to global. The output is gonna be equal to 3.
Okay. Oof. I feel like that's a workout, but yeah. Cool. And if we see here, whenever you look for the 4th number in the Fibonacci sequence, the value is 3.
Yeah. Correct.
Just like cool. So that's kind of crazy what we just did there. Does that look familiar to anyone? This kind of shape? SQ, go for it.
Oh, I think I raised my hand before you asked your question.
Oh, okay.
But yeah, I guess it kind of seems like a pyramid scheme, like linear recursion, right? Where we go like in the linear fashion, then we work back, I guess, backwards, right? But
yeah.
Is that the answer to your question, by the way? I think it's what you
Pyramids, I prefer that answer from now on. That's the answer I want. What was your initial question though, before I shoehorned you into that?
So maybe it was just a mistake, but I just wanted to make sure. In the local execution context where you open fib of 1, you put 1 is equal to 0 as correct, but was that just a mistake, or I think I maybe read it wrong? Yeah, left.
Where did
in the middle, the second one, and yeah, right there.
Oh yeah, that's just a typo.
Okay. I just wanted to make sure I wasn't going like crazy.
No, good catch. It's just like, yeah, that's just that line where it's evaluating. You do this check is 1, 0. I don't know. It's a lot of repetition. This is exhausting.
I get it. Thank you.
Good question. Good looking out. Scott, did you have an answer for what this shape kind of looks like though?
Yeah, I was going to say a tree structure.
It's a tree structure. Yeah. So whenever you have 2 functions calling like a double recursive call, it kind of makes a tree structure. If you space it out like this, you could also non-space it out like this, but I think it's helpful to see it in the tree. It looks very much like a little binary search tree. Except I didn't follow binary search tree rules where the smaller thing has to be on the left. So no one tell Google I did a binary search tree bad. Okay, cool. Any questions about Fibonacci? That was really, really well done, Jose. That way to power through a very long function. SQ, new question or residual hand?
Oh, sorry, residual. Sorry about that.
No worries. Okay. Going back to our little slides, just a little recursion. Recursion is a nice little alternative to looping whenever we are solving self-repeating tasks by invoking the function again and again. When a function calls itself, a nested function level execution context is created, as well as a new stack getting pushed onto the call stack for us. The thread of execution is going to enter that next nested execution context, and all other execution will be paused until we have a resolution. So back here in our linear recursion, this got paused until we solved for this, which called another function. So then that got paused, and so on and so forth. Everything gets halted until until you have finished the execution. And then whenever we reach our base case, the smallest instance of a problem, we pass the return value to where the function was called, all the way down to the initial call site. So that is that bubbling up. That is getting to the front of the taco truck line and having them turn around and say 0, and then adding on back to that until you get to your place in line. Everyone have a good night. Lovely hanging out with you all. Thanks for being so attentive and participatory. See